Hello, welcome to this lectures of week 7 on the course Linear Systems Theory. So far, okay, we did a bunch of stuff building up to concepts in the last 6 weeks, starting from modeling to some concepts in linear algebra. We had studied notions of solutions to equations, equilibrium points, stability, and also how to verify stability in the LTI case. So, we had some kind of Lyapunov functions, we had an energy based or physical interpretation of those. So, today we will talk a bit about control. So, much of the undergrad course focused on say compensator designs using say PID or the lead lag compensators, or at some point of time we also talked a bit about pole placement, right. And in much of the cases we never ask ourselves the question, is the system controllable, right. I just start with the assumption that the system is controllable and then go about designing lead lag or PID controllers or whatever, right. So, you can either through the root locus method or through the frequency domain methods via the Bode plots. So, today we will do a little more qualitative analysis of systems. So, what does it mean by controllability of a system? Is controllability a binary yes or no answer, or there is a little more information to it? What happens if a system loses controllability? What happens if the system loses controllability? What happens to those uncontrollable modes? Are they stable? Are they not stable? And so on. So, we will answer a few of those questions. We will also look at then some tools to test whether the system is controllable or not. Some of them you would have read a bit earlier, like the Kalman-Rank condition and so on. So, we will do a little more detailed analysis on those, because we are now equipped with some tools from linear algebra in the form of looking at systems as evolving over vector spaces, subspaces and so on. Okay. So, we begin with a little example of I will start with a balanced mechanical system. Well, we would have seen a lot of these in real life. So, a balanced system is a mechanical system where the center of mass is balanced about a pivot point. Example is a Segway scooter, where it is just a motorized platform to stabilize a person who just stands on top of it, and when the person leans forward, the device propels itself along the ground, but still maintaining the upright position. So, the person standing on top does not fall, but he can still move forward. So, you could have seen this in many places on TV or also on real life. Another day-to-day example that we do is just of balancing a stick on a person's hand. We would have done this a lot. Okay. So, if I were to model that or look at a simpler version of that, that would just look like or a Segway scooter can approximately be looked upon also as a pendulum on a cart, where okay. So, I can move this cart via a force here. Not only can the cart move from say a point A here to some point B here, this force also helps in stabilizing the position of this mass to the upright position, or as close to the upright position as possible, especially when we encounter certain disturbances. Okay. First is how do we model this? So, much of in one of our earlier lectures we talked of Newtonian mechanics or even the Lagrangian mechanics. Okay, I am not going to teach you Lagrangian mechanics, but just to teach you of how to write down equations of motion through Lagrangian or the Euler-Lagrange equation. We are digressing slightly a bit, but that should be okay. So, if I look at a system, so the Lagrange equation for non-conservative forces is given by this equation, where in this case a q would denote the generalized positions, q dot would denote my generalized velocities, could be both linear and angular. L denotes the difference of the kinetic and the potential energy, and F represents some kind of non-conservative forces acting on the system. Okay. So, what does this mean in the context of the Cart pendulum system? So, I will have kinetic energy corresponding to the mass m here, I will have kinetic energy corresponding to the mass m here, and also this little thing here which would have its own moment of inertia and therefore have its own kinetic energy. So, the total kinetic energy would be half m x dot square, half m for the small mass, and then to do with the theta. And similarly, I have a certain potential energy of the system, right. I just take T minus V, plug it in here, and I will get the equations for the system which looks like this. Okay, you could just work this out. These are simpler techniques to work. So, these are the equations of the system with its coefficients corresponding to viscous friction, the moment of inertia, and so on. And this is the system that we would like to be balanced. Okay, so I can write down the dynamics now in the state space form, which essentially turns out to be a non-linear equation. I just do some little simplifications and then end up with equations like this, and I can assume that I can measure the horizontal position and the angular displacement of the pendulum also, which is sitting on the cart. So, this x will denote the motion of this mass here on which. So, this is the x which I can measure. Okay. So, okay, what are we interested here, right? So, much of the time the problems were spent on can I stabilize this to theta equal to 0 without really worrying about this thing. Now, if I talk in terms of a segue, what I really want is to move from a certain point A to certain point B while keeping theta equal to 0 or as close to 0 as possible, so that the person who is standing on the scooter doesn't fall over. Okay. So, that is a little control problem that I can ask instead of. So, I have a stabilization problem of keeping the mass or the pendulum at the upright position, or the person standing on the scooter at the upright position. In addition, can I ask the question, can the system be moved from one stationary point to another by appropriate application of forces, right, through. So, this is my input here. I don't have any control on I don't have another input here, right. So, if there was another set of input here, then my problem would have been much easier, but unfortunately we do not have any control over this part of the system. Okay. Okay, now this gets us to defining the notion of controllable and reachable subspaces. Okay, why am I using two different terms for controllable and reachable? Okay, that I will shortly tell you that, but we will look at each of these definitions or these properties in terms of some general subspaces of Rn, if n could be the vector space where my system dynamics evolves on. So, what is the problem? So, I have a system x dot is Ax plus Bu, could in general be LTV or even LTI. I know the solution looks something like this, right. So, I start with an initial state at t equal to 0. What I want to reach is a final state x1 at t equal to t1, right. And then, so what does the solution tell me? Well, can I reach, so starting from an initial state, can I reach x1 by some application of control, and this is how the solution looks like. Okay. I do not really look at how the outputs look like, because okay, they are not really important in looking at the evolution of states, right. So, we are just looking at the first equation here. Okay. So, I will not define reachability or controllability yet, but I will just define first in terms of subspaces. So, if I am given two times t1 and t0 greater than 0, the reachable, right, or okay, it is also called controllable from the origin. So, what do I mean? Okay, I am say from the origin. So, this is my origin 0 comma 0 if I am in R2 on t0 t1, right. So, given two times, the reachable subspace consists of all state x1 for which there exists an input u, right, defined over this interval such that, so k is my, number of inputs. So, u belongs to certain r k that transfers the state from this origin to some other state x 1. So, what does it mean? So, starting from here, can I, what are the points I can reach? Can I reach this point by application of some control in finite time t 1? Can I reach this point? Can I reach this point, this point, this point, this point, and so on? And what I do is, so there is no restriction on the input as long as it is bounded. So, I just take the set of all points, and then that set of all points that I can reach from the origin to the point at time t 1 with application of some control u is called the reachable subspace, right. So, that's the mathematical expression of this, that r of t 0 t 1. So, what are the points I can reach starting from t 0 at the origin to x 1 which is at t 1. So, the set of all x 1 for which there exists an input u such that x 1 satisfies this. Okay, where does this come from? This just comes from substituting x 0 equal to 0 here, right. I am just talking of reachable from the origin. It can also be generalized to some other non-zero point, non-zero initial condition, but that does not really change the analysis because I can just shift my origin accordingly, or just for ease of notation and computation here I am just doing that, but in general we can start from any other non-zero point. Now, similarly, given 2 times t 1 t 0, the controllable to the origin. So, here I look at a different point, right. So, let us say I want to reach this point, I want to reach the origin, okay, and I take all the points. So, I take this point x 1 and I ask a question, can I reach the origin starting from this point? I take this point, can I reach the origin starting from this point and so on, and then I do a collection of all these points, right. So, that is what it means. So, the statement says that given 2 times t 0 and t 1, the controllable subspace consists of all states x 0. So, these are all my initial states, right, x 0 for which there exists an input u that transfers the state from any of these x 0s to the origin, right. So, at x of t 1, at x of t 0 I start from any of this point x 0, and at x at t 1 I should be able to reach the origin. So, the collection of all these x 0s which transfers me to the origin in finite time t 1 with some application of control is called the controllable subspace. Okay. Again, this comes from the equation again. So, what is now the final state? Final state x 1 is 0, right, and then I just look at all the initial conditions for which there exists a solution to this equation. We will see what the solution to this equation means in terms of controllability or reachability and their appropriate subspaces. So, the reachability, so the reason I call it controllable from the origin is, can I control starting from x 0, can I go to this point, right. So, it is like, so here I am controlling to the origin or controllable to the origin. I am looking at all points where I want to go to the origin, and then I am looking at, when I say reachability, I am looking at all the points which I can reach starting from the origin. So, usually it is like reachable from the origin or controllable to the origin, and we will quickly see if this subspace. So, is there any relation between the controllable subspace and the reachable subspace, right, which intuitively you could say that if I can starting from this point I can reach. So, this is my x 0 at the origin. If I can reach x 1, I should be able to again start at its same x 1 and then come back to the origin intuitively. We will see if that is really true or not, for what kind of systems that is true, if at all, if it is true, and if it is not true, why it is actually not true. Okay, so let us begin with an example. So, I have this parallel RLC circuit whose dynamics I can write in this way. Straightforward to compute, just apply the voltage and current laws that we know. Okay, so I am looking at the solution of this, right, for some input. So, x of t, we have some initial conditions, and then you have this term here. So, I am just writing down this term over here. Okay. Now, assume the R's and the C's, the resistances and the capacitance are such that they have the same time constants, that 1 over R1 C1 is 1 over R2 C2, and let me call that omega, right. In that case, my solution x of t will be something like this, e power minus omega t times omega times this one. Okay. In the reachability analysis, I am interested in x 0 is 0, and therefore, what I am left with here is the x of t, the set of all x of t that I can reach starting from the origin takes some form like this, right, some alpha t, a 1 here and a 1 here. Okay, if I just write it down, so x 1 t is alpha t, x 2 t is also alpha t, right, where alpha t is just this one. Okay. So, what does this mean? If I were to plot the reachable subspace, so if I just say, well, here x 1 is equal to x 2. So, the points I can move or I can reach starting from the origin is only on this red line, which also means that I cannot go to this point or this point or this point. Okay. So, I am restricted, or my movement is restricted only to this red line, or it also means the system cannot be transferred to any state with x 1 t not equal to x 2 t. So, I cannot have that I want to go to a point where x 1 t equal to 1 and x 2 t equal to 2. Whenever I say x 1 equal to 1, I am immediately impose the condition that x 1 should be equal to x 2, right, from this equation. Okay. So, I cannot, or the system cannot be transferred to any state where x 1 is not equal to x 2. And therefore, okay, if I look at this reachable subspace, the reachable subspace is of dimension 1, right. So, the reachable subspace is of dimension 1, right, which is again a subspace of R2, and my state space is R2. Okay. Similarly, I can do the controllable part, right. So, what are the set of points starting from some initial conditions which can reach the origin. Okay. So, it again turns out to be the same, that the controllable subspace, well, it will again be the same, right, because if I look at this one. So, again I have a x 1 is alpha, x 1 is alpha, x 2 is also equal to alpha. Okay. Therefore, the controllable subspace also reaches also looks like this. So, all the points that can be controlled to the origin will have some form like this. Okay. So, what does this mean? So, let us say I have two cars, say this is car 1, this is car 2, okay, and then I have the same input force which is being applied to both the cars. Okay. Now, the point is, okay, can I take this car to a destination A and can I take this car to a destination B? The answer is no, right, because I mean, assuming all the properties are identical and so on. So, this force acts equally on these two cars, and therefore, I cannot take this independently to some other location and this independently to some other location, or I cannot control both of them individually. Whereas, if this is the case, C1, C2, I have a F1 here, I have a F2 here, I can actually take each cars wherever I want. So, this is a little interpretation of this. Okay, what happens if the time constants are not the same? Then we will have a better looking solution, that I can actually reach all the points in the state space here, here, here and so on. So, we will eventually come up with conditions of what is the dimension of the subspace, or what are the points I can reach starting from the origin, if at all I can reach. Okay. So, that will be the objective or the larger objective of this lecture. Okay. So, now I define what are called the controllability and reachability Gramians. Okay. The definitions will be clear as we do the proofs and understand them. Okay. So, given two times, again T1 and T0 greater than or equal to 0, the reachability Gramian, and they are defined something like this, right. I know the phi is the state transition matrix, B is the input matrix and so on. So, this is how I define. Well, let us assume that this is that I know that this is true. What is the motivation for defining it this way? We will slowly come to that while we do a bit of the proofs. Okay. So, once I have this reachability and the controllability Gramians, okay, they will have some properties of their own. So, just check for yourself from the properties that we know, will the reachability Gramians, if I compute this, will they be sign definite in the sense of will they be positive definite, negative definite, or I just cannot say anything about the sign of them. Just a little trick question that you can infer from maybe lectures from week 3, right. Okay. So, what am I interested now, right. So, given a system x dot is a t x t plus b t u t, how do I compute the reachable subspace? So, this question answers this theorem answers that question. So, again given 2 times, the reachable subspace is just the image of the reachability Gramian, this one, sorry, this one, right. So, if I just take the image of this map, that will be my reachability Gramian, or that will be my reachability subspace. Okay. Moreover, if x 1 belongs to this W r, so times eta 1 with this x 1 belonging also to the image of W r, then the control u t given by B transpose phi transpose eta 1 can be used to transfer the state from x t 0 to x t 1, right. Okay. So, what is given to me? What I want to prove is that the reachable subspace or the reachable space is the image of W r, right. So, when x is in the image of W r, there will be a vector eta 1 which will transfer eta 1 via W r to x 1, and then okay, this and what is the control? This is the control that actually transfers my state from origin to some x 1. Okay. So, okay, the proof sketch, well, we will first start by showing that if x 1 is in the image of W r, then this same x 1 is also in R of T 0 T 1. Okay. So, what does that mean? So, we will just write down the proof for ourselves. Okay. First we start by showing that if x 1 is in the image of W r T 0 T 1, this would also mean that the same x 1 will belong to the reachable subspace. Okay. So, what does it mean when x 1 is in the image of W r T 0 T 1? This means that there exists some vector eta 1 in R n such that this x 1 is W r T 0 T 1 times eta 1, like the definition of the image. Now, we need to show that, or just check, does this x 1 also belong to R of T 0 T 1. Okay. So, which means that if this x 1 belongs to R of T 0 T 1, it should mean that starting from this point, from the origin, I should be able to reach this point via some application of control. Okay. Now, what is that control? That control is given in the theorem statement, this control, this guy. So, this control law u of t is B of t phi transpose T 1 comma t eta 1. Okay. So, this should be a transpose here also. Okay. So, now I will just check it, does this control law transfer my system from the origin to this point x 1. Okay, that should be easy to check. from the solution. So, x of t1, okay, so what do? I just substitute all of this into the solutions here. Here, right. So, I know what is the input u, I know that x of t0 equal to 0 and I compute what is x1. Okay. Okay, what does that give me? X of t1 is, okay, the initial condition x0 equal to 0. So, the first term goes away, is phi t1 comma tau b tau b tau the transpose of it, phi t 1 comma tau again the transpose of this times eta 1 d tau. Okay, now look at this carefully, this expression in the dotted box okay, this expression in the dotted box is essentially the reachability Gramian. Okay. So, this x1 is equal to WR times x1. Okay. So, again let us go through the steps again. So, what I know is that x1 is in the image of WR, okay, which means something like this happens. So, this is given to me. Now, what I want to show is that with the application of this input u, does this transfer my system from an initial condition which is the origin to x1, sorry x of t1 is x1. Okay. So, in the solution I just substitute the value of u and what I get that this x of t1 is nothing but, okay, this should be an eta 1 here, is, sorry, this x at t1 is WR times eta 1. Now, what is WR times eta 1? WR times eta 1 is precisely my x1. Okay. And this x1 is in the image of WR. So, what did I prove now? That if x1 is in the image of WR, the same x1 is also in the reachable space, because I can reach this point. So, by application of this control starting from the origin, where do I end up with? I end up at precisely this x1. Okay. So, the first thing is done, right. So, the x1 which belongs to the image of R also belongs, so the image of WR also belongs to the reachable space. So, if I just say, okay, this is my x1 which belongs to the image of WR, it also belongs to the reachable space. So, this picture also means that the image of WR is a subspace of R T0 T1. Okay, it could be something like this. Okay, now the second thing that we need to show is, okay, let us assume now that x1 is actually in R of T0 T1 and show or check if this x1 also belongs to the image of WR T0 T1. Okay. Now, okay, what does it mean when x1 belongs to R T0 T1? So, when x1 is in R T0 T1, this means that there exists an input u, could be whatever, right, for which x1 is integral T0 to T1 phi T1 comma tau B tau U tau D tau. Okay. Now, what I would want to show is that does this mean or does this x1 belong to the image of WR? Okay, let's show this. Okay, now some things that we know from our previous lectures is something like this, right? So these two things here, this and this, right? So I will just quickly write down those here in with respect to the theorems that we will do here. So if I were to show that x1 is in the image of WR T0 T1, this image of WR is also equal to the kernel of WR T0 T1 with its perp. Okay. I assume we can recollect what is the definition of this perp here. Okay. If not, then I can just write down. So this is the orthogonal complement. Okay. So if I take a subspace V, its orthogonal complement V perp is the set of all vectors. So this V perp is the set of all vectors x in Rn, assuming that V comes from Rn, such that x transpose Z equal to 0 for all Z in V. Just recollecting the definition that we had earlier of the orthogonal complement. Okay. Now, what do we need to show? So, again we know that x1 belongs to the reachable subspace, which means something like this holds. Now, what I want to show is that this x1, which is an image of WR, which is also equal to the kernel of WR with its perp. So, okay, sorry, I need to show that this x1 is also an image of WR, which is equal to the kernel of WR with its perp. Okay, which means that we need to show whether something like this is true, x1 transpose eta 1 equal to 0 for all eta 1 which come from the kernel of WR T0 T1. Okay. Now, so this is what we need to prove. Okay, how does this x1 transpose eta 1 look like? X1 transpose eta 1 is, okay, what is x1? X1 comes from here, and if I do the transpose, it will simply be T0 to T1 U with its transpose, B with its transpose, phi with its transpose, eta 1 d tau. Now, this eta 1 is in the kernel of WR, which means that if I define a quantity like this eta 1 transpose WR T1 T0 eta 1, this will be nothing but T0 to T1 eta 1 transpose phi T1 tau B tau. Then I have B transpose tau phi T1 tau transpose eta 1 d tau. Okay, that comes from the definition of the WR, the reachability Gramian. Okay, so if eta 1 is in the kernel of WR, okay, just to simplify this, I can also write this way, right? T0 to T1 B transpose tau phi T1 tau transpose eta 1 square. Now, this is equal to 0 because eta 1 is in the kernel of WR. Okay. This also means that the quantity inside this, which is B transpose tau phi T1 comma tau eta 1 equal to 0. Now, this is valid for all tau in T0 T1. Okay. Now, again go back to this expression of what was x1 transpose eta 1. x1 transpose eta 1 was T0 to T1 u tau transpose b tau transpose phi T1 comma tau transpose eta 1 d tau. Now, look at this expression closely. So, this thing here b times phi times eta, the 1 is equal to 0, sorry. Okay. And so, this is equal to 0, and therefore, x1 transpose eta 1 is also equal to 0, which is what we wanted to show, right. Okay. Again, let's go through the proof again. What we wanted to show is that if x1 is in the reachable space, which means there exists an input u such that this equation is satisfied, then we need to show that this x1 is in the image of WR, and the image of WR has a form like this. Okay. So, equivalently this means that we must show that if x1, okay, which comes from the reachable space, if it has to be in the image of WR, it should satisfy something like this. Okay. Where eta 1 comes from the kernel of WR, or the reachability Gramian. Okay. So, now x1 transpose eta 1 expands in this way, right, this one. Okay. Now, making use of this fact that eta 1 comes from the kernel of WR, I compute eta 1 transpose WR times eta 1, which is 0. This being 0 also means that B transpose phi transpose eta 1 is also equal to 0, right, which actually sits in very well in the computation of x1 transpose eta 1, and therefore, x1 transpose eta 1 equal to 0, which means that if x1 is in R T0 T1, it implies that the same x1 is also in the image of WR. Okay. What does this mean? So, I have a x1 here, this is in R, and this x1 is also here in the image of WR, which means R T0 comma T1 is something like this. What does the first expression tell me? Well, it tells me the opposite, right, that the image of WR is a subset of R T0 comma T1, and this is possible if and only if R T0 T1 is the image of WR T0 comma T1, and this is what we wanted to prove, that the reachable subspace is the image of the reachability Gramian, right. That was what the statement was, that R of T0 T1 is image of WR T0 T1. Okay. So, similarly I can do for the controllable subspace, that the controllable subspace is the image of the controllability Gramian, which is defined this way, the second expression here. Okay. Okay. Nothing much changes in the proof steps. So, I would leave the details to you. So, again the theorem statement says that okay that C the controllable subspace is the image of WC, and moreover if x0 is in the image of WC T0 T1 the controllability Gramian, the control U of t, which is now okay, what was it earlier? It was B transpose phi transpose eta 1, now it is just with the negative sign. U of t is minus B phi eta 0. This can be used to transfer the state from x at any initial condition to x t 1 equal to 0. Okay. What does this mean? So, so I am just looking at a control law which will take all points x 0 starting from here till the origin. Loosely speaking, if I can go from here till here with say some force or some application of input u, it can be thought of that if I want to come back, I just apply a force of minus u, right. So, this way I apply u, this way I apply minus u, and that is a loose interpretation of why this minus sign is sitting here, and the rest of the proof follows exactly the same steps. So, I will skip that over here. Okay, so let's do a couple of examples on how to actually compute this. So, I have a LTV system where A of t looks like this, B is like this. So, I am just computing, okay, I will ask a different question, not is the system reachable, I will just compute what is the reachable subspace before computing is the system reachable. So, based on weak force lecture, I can compute the state transition matrix to be of this form. Okay. Now, I know that B is given in this form. I compute the reachability Gramian. The reachability Gramian is a 2 cross 2 matrix of which looks like this. Okay. The rank of it is, well, you can just say that it has a maximum, have a rank of a maximum of 1, right. And therefore, the reachable subspace is at best 1. Okay. And therefore, the system is not, I would say, completely reachable. So, the reachable subspace could be as in the starting example we did, right, some subspace of one dimensional subspace of R2. So, we call the system completely reachable if it reachable set or the reachable subspace is of the dimension of the state space, which is 2 in this case, right. So, we can conclude that this system is not reachable. Okay. Now, I do a little simpler case of an LTI system where again I compute what is e power at. This is my state transition matrix in the case of an LTI system. The reachability Gramian takes this form, and well, I can look at what is the rank of this. The rank of it is non-zero for all T1 greater than T0. This is what we want, right. We do not want to start at T0 and end up at T0, that does not make sense. And therefore, the reachable subspace is of dimension 2, and therefore, we can say that the system is reachable. Okay, you can do these computations, they are pretty straightforward to do. If I were to go from point A to point B, I would want to go with a minimum possible energy, right. I do not really want to overuse my energy resources. So, what is the minimum energy that transfers my system from point A to point B? Okay. So, we will just look at the theorem statement and say, well, what was the input that we used earlier? The input that we used earlier was this one, U is B transpose phi transpose eta 1. Okay. Now, let me check if there is some other input, right. So, let us start with the reachable subspace. So, let us say a particular state x1 belongs to the reachable subspace of the system. Okay. We know that if it is in the reachable subspace, there a certain control input takes it to this state u1. Let me assume now that there exists another u bar which also transfers the system to the state u1, this one, right. I can reach the state x1 with u or also u bar. Okay. Now, if this is true, well, I can just do subtract and say that, well, this condition is also true, that phi b V transpose is V of tau times d tau is 0, where V is just the difference between u minus and u, sorry, u bar and u. Okay. Now, if I just look at the energy, right, which is can be interpreted as a 2 norm, let me calculate the energy of this guy u bar. U bar can take this form. So, I know what is u. U from my previous equations is this one, if I am talking of reachable subspace, this one. So, I will just write it down here, u is B transpose phi transpose eta 1. So, u is B transpose phi transpose eta 1. Okay. Now, I am just looking at, okay, so what is, so from this expression u bar is V plus u. Okay. So, this is what I get, right. So, the energy of u bar is can be expanded this way. Now, I know that, okay, so I just use the standard A plus B whole square formula and then I get something like this. Okay. Now, what we know from here is that this term is actually 0. Okay. Now, I am left with this term and this term here. Okay. Now, when the question I would like to ask here is, when does u bar take a minimum value? So, the new control input that I use, which is slightly different from what I had defined here, what is its minimum, or when does it take a minimum value? Well, look at this term here, this term W r is always to be positive for the system to be reachable. That is what if I look at the example closely here, if W r is of full rank, then the system is completely reachable. Okay. So, therefore, the W r should be a positive matrix. Okay. Now, this I cannot get this to 0. What is possible is to minimize this term by setting this to 0. So, this the energy of u bar is minimized when V equal to 0. Now, what does it mean from here when V equal to 0? V equal to 0 actually means that u equal to u bar, and therefore, the minimum energy required, if I just say, well, I am just taking some energy and computing what is the minimum energy required, that actually turns out to be this input only, this input u, right. So, the minimum energy required is just given by this expression. Okay. So, that is a little intuition of also why we choose this particular energy here. This is not only steers from point A to point B or x, or from the origin to x1, but it also consumes the least amount of energy, and this is a little proof for that. So, more formally, if I state that given 2 times t1 and t0 which are greater than 0, when x1 is in the reachable state, the control transfers from the origin to x1 with the smallest amount of control energy, right. So, what is the control 8? The equation 8 is this one, right. So, this control input transfers the system from the origin to x1 with the least amount of control energy, which is just given by this expression. Similarly, for the controllable analog of this, when x1 is in the controllable subspace, right. So, the control which is with the negative of what is in the reachable subspace is just given by this expression. So, the idea here, or the main message here, is to say that the control energy which I defined over here in equations 8 and 9 is actually the best or the least energy consuming control signal which will transfer my state from point A to point B, could either be in the reachability analysis or even in the controllability analysis. Okay. So, we conclude this lecture by just recollecting that we computed what were the reachable and controllable subspaces. We defined the notion of the Gramians and then had some proofs on how the controllable and the reachable subspace are related to their respective Gramians, and we also quantified what is the open loop, okay, this is the open loop, right? I am not really closing any loop here, I am not doing a state feedback or something. So, we also quantified how much is the open loop minimum energy required for the reachability and controllability analysis. And next we will go to, okay, what is the controllability matrix and what essentially how do we now define controllable systems. That is coming up in the next lecture. Thanks for listening.